Okay, I think we're ready. You might hear the printer running. It's finishing up one of those little vases I've printed. We've got a couple of things for today mainly. Last time we did the, what did we do? We did the SolidWorks topology optimization. So we made a connecting rod of sorts for a internal combustion engine. So we're going to do the same thing, but in Fusion. Well, it used to be called Fusion 360, but I believe they've rebranded to just Fusion. So we're going to do that today. And we've also got our little capstan pinch roller system that we're going to replace on our printer. I did, remember last time also, I did show you the enclosure. I don't have the printer in the enclosure right now because it would be really hard to actually, you know, put this on if it's inside the enclosure. The enclosure is back here, just so you can see what it looks like. There it is. The light works in it fine. I did print some of our carbon fiber polycarbonate in it, and it worked okay. Well, sort of. So I printed twice. The first time I used the carbon fiber, you know, the little sample that I had been using, and it did print, but it was still, well, here it is, you know, still having problems, right? Actually, is that it? I think this is it. So it's very weak. And I thought that it could be the problems were with the exposure of this filament just to the atmosphere. The polycarbonate filament in general is very hygroscopic, so it absorbs moisture from the atmosphere. We're in a very humid place, so I did get out our new version. So over here, let's see, we can go back to this picture. I did get our new version over here, and it printed much better. So it printed, first of all, it's much darker. So it printed this guy. I'll get it maybe over here so you can kind of see. Right now we're printing that. So that's what it looks like. Really nice. Now, I don't know if you can tell or not on here. Yeah, you can tell right there. So these first couple of layers, I don't know if I can get it to focus on that particular part or not. Maybe. I printed it at the hotter temperature. So one of the things for originally, you know, I wanted to do was I wanted to print hotter because I thought this material needed to go up to 260 or 270, and the other material that we had printed was at that. This is a different version. Let me see if I can find the box. Oops, sorry. We'll have to get our camera. There we go. That's the name of this carbon fiber polycarbonate. And when I got to printing it at that hotter temperature, it was printing, but you know, it's rough compared to this temperature. I wish I could get it to focus more cleanly. There we go. Now I'll have to refocus it later, but this temperature here is 240. So you could print that on a standard Ender 3. It's at the upper end of what you could do, but you could print that. Now, I put some, I think I put them in, I put them on canvas. I'll have to go back and add them to the YouTube description, or maybe put them in chat or something. Maybe I'll do that so that I think I can, well, we'll see how much I can put in chat. I'm not sure. Let me see if I can grab the settings I used. These are adapted from a user on Reddit. So they may have gotten them from some other place, but here are the let's see. Here are the settings. Let's see if I can put all this in chat or not. I don't know. Oh no, it's too many characters. So can't do that. I could do it a little bit at a time. Let's see if I can find, first of all, here are the basics. So I'm using the 0.6 millimeter hardened nozzle. So the 0.6 because this is carbon fiber field, and anytime you've got a fill in an object, in a filament, it's probably better to have a larger nozzle just to avoid clogging. Now this, the field here on this is small enough that I think you could print it just fine on a 0.4, but there's another reason you might want a 0.6, and that is that fill will not allow flow out of the nozzle quite as nicely as if it's just a pure plastic. So you want to print thicker layers to avoid that. So printing thicker layers probably means a larger diameter nozzle. You could probably do a 0.3 layer height on a 0.4 millimeter nozzle and get this to print okay. But what I did was I did a 0.3 layer height, or up to 0.4 even, on a 0.6 millimeter diameter nozzle. Now the other part is it does need to be hardened steel if you're going to print any more than like this amount. If you're going to print an actual object, which our goal was we were going to print a violin. So we've got it to where I think we can start printing that now at least. So that was our goal, and at that amount of material, you'd burn through a brass nozzle with any kind of carbon fiber field filament. So that's the first step. And then I would, now if you don't have a all metal hot end, you can't do this part, but here are my first layer settings in chat. So I did go 270. Well, actually, you know, mine I printed 270 for several layers, which you can see the roughness there. But I think you do want the first couple of layers as hot as you can get. I did use glue stick on a textured PEI bed on the first layer. I also had the bed temp at 100. Actually, I think it was 107, because that was the defaulting cura for that material. So you want hot filament as much as you can get for the first layer, maybe even print slower. So here's some other settings for the first layer. I'm going to put these in chat also. So a thinner first layer and slower. So one thing that you're trying to avoid here is that first layer peeling up, so the nozzle dragging a piece and, you know, peeling up the first layer or whatever. I actually did have that happen on the first iteration of the print. So maybe print a little slower, maybe even a thinner first layer, just to get the first layer stuck down well. We do have our bed sensor. I was using the textured PEI sheet. It's all out of focus now because we're focused somewhere else. But then after the first layer, so you can change, let's see, you can change first layer settings from the other layers in your slicer. You don't have to like try and watch it and change them on the screen or anything. The middle layers, I ended up at 240, and that produced this result, which I like. I think that's good. On the camera, you can't even see the layer lines. In person, you can if you look close enough, but the camera is not. Maybe you can pick them up. I don't know. One of the things with the carbon fiber field stuff is that it gives it a, I don't know, this one's a little bit shiny. So maybe a semi-gloss finish, and it hides the layer lines pretty well. So I printed this at 240. And then I was doing layers I was doing 0.3. A good recommendation from Vision Miner. So they're a company, I don't actually know where they're located, but you can find them on the internet. They have their own printers, plus they print like high-end FDM materials. So more like stuff that's going to be an engineered product. And they have found that a 60% of your nozzle diameter is a good layer thickness when printing carbon fiber filled materials. And the main reason being you don't want to generate that back pressure from trying to squeeze out thin layers of a filament that has some kind of fill in it. So that's where we're at. I'm happy with this. I think I will set it up to where my first layer, since I do have the all metal hot end, my first layer I'll print at 270 again with the bed at, I don't know, 107, 100 again. Oh, also in that enclosure, everything heats up much faster. So remember this bed, the first time I tried printing at a hotter, or maybe even a normal temperature, it was on one of the streams, it took forever for the bed to heat up. But in the chamber, it didn't take any time. I'm going to add, I don't know, maybe in a couple of weeks, one of the streams will be adding a chamber temperature sensor so that we can see what the temperature is in the chamber. It was definitely above ambient. I could tell that just by touching the you know, the window, so that window up there comes down. You could just feel that it was warmer there. And we'll try to print one of our actual pieces here. This is just a single wall print, so we haven't actually, you know, tested any real retraction or anything. This is just a spiral print. So today we're going to install this guy. We don't really need this for anything like a specific purpose, but it is going to give us a little bit more reliable feed into our hot end. I'm not going to do that just yet, though. For one, the printer's still going. But I do want to go in and do the Fusion stuff. I want to do that first because, let's see if I can get it to pull up. There it is. Because if I don't do that first, it does take some amount of time to generate its solutions. All right, printer finished also. So that's not so loud now. We'll go ahead and turn it off. So it does take some amount of time to actually, no, let's not turn it off because we're going to have to get that filament out. We'll go ahead and yank it off out of there. All right. All right, we needed the filament out to be able to change the capstan on the feeder. All right, so now back to Fusion. It does take some amount of time. So SolidWorks, we did topology optimization. We did a connecting rod. You know, something like one of these, this red piece over here. This is just a picture from GrabCAD. So something like one of these, and we had it do the topology optimization. So basically we made a bulky looking connecting rod, specified some features that we needed to keep, and let it do its thing. SolidWorks runs all that locally, and it finished in, I don't remember, 10 or 15 minutes, somewhere in that time frame. Fusion is going to do a similar thing, except that it is going to send your data to its cloud. So I assume it's using a Amazon Web Services type thing. If you have the education license of Fusion, which you should be able to get if you just have a .edu email address, so you might have to apply for it. If you do that, then so far I've had unlimited access, but if you tokens basically, so that I didn't have to pay for any of these simulations in Fusion. But if you don't have the education license, then there's some cost, like a real cost, that you have to pay to do some of these simulations. I don't know what the cost is because so far it's been free. I don't know how long that'll stay, but today it was, or this morning it was. I assume it will be when we do this again. All right. So it's generally the same idea, except that, and you can actually make it almost exactly the same idea, and give Fusion a starter geometry like we did in SolidWorks. But we're gonna avoid that part of it and just do the generative part. So maybe you've never used Fusion before, but this is the screen you start with, and what we want to do is, I've got my little notes on what sizes we made things last time. So I have switched over the units here in the document settings. I've switched them to inches because the default is millimeters, and we did everything last time in inches. So just to make it easier, I'm just going to switch the unit system to inches. So we're going to create a sketch, much like you would do in SolidWorks. And you've got a similar setup here. You know, you've got your three planes. Maybe they look a little different, but it's the same idea. And then you've got the same types of tools up here for sketches, lines and circles and splines and all that. So we're going to create circles. And this one, let's see, D is dimension here. So this one is going to be the inner size of the big end, which we set at 2.1 inches. And then we're going to, got to remember how to move around in here. We're going to, oh, get off of there, draw a circle. We're going to draw the small end, and I did it at 0.9 inches, and we did it 5.7 inches apart. So I remember those. I'm going to go ahead and draw some more circles. So we need one here that is basically the thickness of the wrist pin area. So I don't remember the exact dimension I made that, but let's just say I added half an inch to the total. So if I did 0.9, then that would be 1.4 inches. That looks awful thin. I did do. Did I ever make this one? Oh, I never made this one 0.9. That's why. Okay, there we go. That looks better. And then let's do a similar thing here. Maybe we need this one to be a little bit more beefy. So I made it at 2.1. Let's add ½ inch on either side. I don't know if that's what I did last time or not. So that would be 3.1. Oh, I need to set it first. So there we go. Let's cut off the bottom part here because we don't need that. So I'm just going to draw a line there, and then we'll trim. Whoops, we'll get rid of the line there. We'll trim off that stuff and that stuff, that stuff. So one thing I like, the very first CAD software I used was Autodesk 10 or 11, something like that. It was a long time ago, in 91 or 92, so a long time ago. And so I learned a lot of the keyboard shortcuts for, you know, a circle is C and a line is L, dimension is D. So all those kind of, they're not like hard to learn. They're pretty obvious. And all of those transfer over into Fusion. So if you know anything about Autodesk already, then you will know a lot of your shortcuts. And I just realized the way that this is going to work, I actually do want a circle here. I do want a circle here. Then that's a function of how Fusion is going to do the generative design. So I do want a circle there. Let's see. Let's go ahead and finish these and make these into bodies and not just sketches. So this one and this one, these are going to be occlusion zone. So I don't want material here at all. So I'm going to E to extrude these. I'm going to extrude them two-sided, and an inch in each direction should be fine. That's fine. So these are basically going to be area volumes, not areas, but volumes where the generative design is not allowed to put material. I need to get that sketch back because now I want these guys. I want these to be like you have to put material here. So I've got the wrist pin area up at the top, and then the bottom half of the big end. I need some material there. So I'm going to say that these are two-sided, and I want them. Let's see. Yeah, you can see that. I want them to be. I made them 0.94, so I want half of it on each side. So I'm just writing the equation 0.94 divided by 2 on either side. I don't want this to be joined though. I want these to be new bodies, or I could do new components, I guess. And then we can turn that sketch off. So now I've got some volumes where you have to have material and some volumes where you can't have material. I think the other thing I added to our other one was that we do have to bolt the end cap on here. So we made some bolt holes. So maybe we'll do that on this one too. So let's just say that we want to have, let's just make it really simple. We're going to create a sketch on here. Okay, it's going to rotate it around that way. And we'll put a, let's see, drive it from the center. I wish it would grab the edge of that. Oh, okay. So let's see. Got to remember how to do this. Create, include, I want to include that line on in my sketch and that line in my sketch so I can get the center point of them. Alright, so now when I create a circle, I can actually find the center of that. There. And there. Now I've got the little half circles. That's fine. I probably should have gone ahead and made that. We'll come back and make the oh, did I finish? Oh wait, extrude. We'll come back and make the holes. We'll extrude this something like that, but this is not going to be a cut. It's going to be a join. We don't want that to be a new body. We want it to be part of that one. So, okay. And now let's go back and let's put the holes in there. So we could have done that at the other step, but I didn't. So I want to find the center. Oh, a circle. And we'll scale them here in a minute. Where'd the center of that one go? Well, I can't find the center. I'm going to have to force it to do that. There we go. All right, so we want these. Let's make them. I think I made them 1/4 inch. No, that looks really small. Did I make them 1/2 inch? Sure. All right, and then we will pick those guys, extrude them through there, cut them out. All right. Oh, did I not select? Ah. I think I didn't. Somehow I didn't select that one. There, we got it. There we go. All right, so there's our starter geometry. All right, so assuming that you've got the education license with the full set of packages of, you know, there's a simulation thing in here, there's manufacturing, animation, rendering, all kind of stuff, but there's one called Generative Design. So I'm going to select that one. And it gives me, do I want to generate a structural component or some kind of fluid path for a heat exchanger or something. So we're going to do a structural component. Okay, so it brought in all the geometry that I have been working on. And you can look at it one of two ways. So over here in the tree, you just kind of walk through these steps, or across the top, you can walk through the steps left to right. I guess the guide will either turn this on or off. So we've already set up that we want a new generative study. I guess we could, let's look what they're in the settings. Oh, all right, so you could have a higher or lower outcome. We'll just leave it in the middle for now, because I do want to see the results sometime during the stream. So we'll leave it there. We could go in if we wanted to edit the model in any way, but we've just done that, so we don't need to do that. So preserve geometry. So are there any pieces of geometry that we've made that you have to have in the final result? So there are, and we want that body and that body. We have to have those because they're part of the design. And you could go in, you know, we didn't do any filleting or anything like that. We probably should, but we're just trying to make it simple. So they'll turn green. Obstacle. Are there any things you have to avoid? So this guy and this guy, there cannot be material there. Also, ooh, I should have made it where that bottom surface can't have material on it. So I really should have added a little platform here that would make it where there's no material below this line. Hopefully it won't try to generate any there, but I don't know. We'll find out. Probably should have put a occlusion there, but I didn't. Here is, in SolidWorks, we had to build out a blank, sort of, and then it ate away at that. I could give a starting shape here, you know, other than what I've already drawn. I could have something between these and have it, you know, I kind of want it to look like this and work on that, but I didn't do that, so we're going to leave off the starting shape. Do you have any symmetry? Symmetry will speed up your solution and control that you have some, you know, your part is not asymmetric. So I do have symmetry planes. I will have to show them though. There's going to be one there and one there. So I'll have a quarter model symmetry. That's the same thing we did in SolidWorks. Obstacle offset. So on these obstacles, is it that I can't be in that volume, or I can't be some distance away from that volume? So in this case, I've made them the exact size, so I don't need to offset the obstacle. Constraints. So our big constraint will be that surface, and we got to pick this surface in here, which, oh, I had it. I know there's a, you can select more faces. I don't remember. There we go. Just hold down that one. So if you hold down the select button or your mouse button, then it will let you select the one you're trying to get. So those surfaces are going to be constrained X, Y, and Z. They can't move. They're fixed. Okay. We're going to put a load, and I probably should have put a split plane in here so that I'm only putting the load on the bottom part of this surface, but we're going to put a load on that surface. We're going to make it go downwards. I don't know why we're in newtons, but let's change units to pound force. We put 10,000 pounds on the SolidWorks version, so let's put that here. And then we could, you know, if it's at an angle or anything, we could do that. Okay. I don't need either of these. So what are our objectives? So do we want to minimize mass or maximize stiffness? There was in the SolidWorks, it was kind of the ratio, is the stiffness ratio. So here I have to choose one or the other. I'm going to do minimize mass. And then if I wanted to avoid some frequency, or, you know, find some minimum first mode frequency, which probably is important in the connecting rod, I could do that. Or some minimal amount of displacement, I could do that. Avoid buckling, definitely want to do that. So you could select as many of those as you want and give them their own criteria. We're just going to say minimize mass. If I do maximize stiffness, I can also give it a target mass. Maybe let's do that, because that was one of our goals. I think we wanted it to be 0.35 kilograms. So we wanted it to be 350 grams was our goal last time. So let's do that, and then keep the stiffness. That'll kind of do the stiffness to mass ratio, weight to ratio. Let's see, do we have any? Oh, manufacturing. So what it's asking us here is there are 3 types of manufacturing. Oh, well, I clicked off of it. Let's go back to it. 3 types of oh, no, 4, because I can include casting. So I can have casting, 2-axis cutting, so like milling from one direction. Cast something that's castable, meaning I've got draft angles and all that kind of stuff. Milling, but I can describe which direction I want to mill from, and I could mill from multiple directions. And then additive, so I could 3D print this thing in a variety of directions. And right now it's just X, you know, if you look, oh, it's under your screen, under my picture. This would be the orientation where it prints it kind of flat. I can't get it to, there we go. It prints it kind of flat in the current orientation here, which would kind of mean, and it's going to try and avoid certain levels of support. So you see overhang angle here. You tell it what your maximum overhang angle is before it needs support, and it'll try to create a part that doesn't need support. You tell it what's the minimum thickness of any part, you know, that you can resolve on your printer, and it'll not make any features smaller than that. So let's not do unrestricted, because that could give us a lot of things, but let's do additive, and let's do milling. Actually, let's do 2-axis cutting, so like water jet cut or something. We'll give it 2 different options here of things it can do. Actually, I want to see what the casting does, just to see. Our minimum thickness on this is probably more than that, though. Hold up, huh. There it goes. It's acting really slow all of a sudden. Let's do a minimum thickness of 5 millimeters. Alright, so it's going to go through these 3 processes and try to create some geometry that's suitable for each one of those. We do need to tell it what materials we want it to consider. So all methods, they need to be metal, and let's put aluminum in there, and 304 stainless. So now, and we could specify, oh, for this method, only consider those materials or whatever, but we'll just do this. I don't want to make it overly complicated. Now we go in here to generate, and it's got a little pre-check. Oh, 2-axis. All right, so oh, you know why? Because I think it can't make these curves here. And I told it had to make these curves, but the 2-axis, these would just be like flat. So maybe let's get rid of the 2-axis, because we wouldn't water jet these. So let's go to manufacturing and just do casting versus additive. Okay, so it gave us a little warning. Pre-check says, okay, now we're good. And that's okay. We can do a preview. I'll try to do a preview. So the preview runs locally, and it'll give us just kind of an idea of what we're going to end up with. I'm not sure exactly how long it's going to take to preview, so we'll see. If it takes too long, oh, okay, so you can kind of see there's its first thing. So basically, first of all, it just connects everything together, and then it starts eating away at it. So it's iteratively running finite element analysis on this geometry. Oh, you know what? I did notice that I told it to preserve this green, but I didn't tell it to avoid filling in these holes. So it might fill in these holes here, but that's okay. We could fix that easy enough. So, you know, that's kind of what its first pass is going to do. It did generate some holes in here, but it didn't completely avoid them. So, you know, maybe let's go back. Okay. And let's go to our design. Oh, wait, let's see. Here's a hole. I want there to be start of shaft there, and I can only do one at a time, and end of shaft there. And let's include room for the bolt head, but on the bolt head will actually not be on this piece, but so we'll leave that off. I haven't actually done this part before, so I'm kind of like, oh, okay, that looks good. Let's see what happens. I think I'm just telling it where I want a hole to stay. It kind of filled them in, not sure. And it filled them in red. Alright, so let's do our pre-check again. Okay. And then we will generate. So we could do the preview again, and all it would show is that it didn't fill in those spots. It might fill in over the top of them, though. Let's see, generate. So here is where it is going to send this off to the cloud. So it says it would take 11 cloud credits. I don't know how much a cloud credit is. Maybe we can do a little search on that and see. Right now I have unlimited cloud credits, so it'll be fine. So we'll generate one study. And this will be, this is MEN 432 Conrad. Okay, and so we can kind of track what's going on here once it's satisfied that it can actually send this out. So it's sending, and then once it notices that it's successfully sent our design off to the cloud, then with all the constraints and materials and all the manufacturing processes, then we'll start having an update here. Right now it's scheduled, so it is under my, you can't see it, but under my picture it shows that the it has started successfully, and you can see thumbnails will appear when they're processing, so that's good. So once we get to some place, we'll close this window, we'll get some samples of what it's thinking. So that's going to take a while. So while that's happening, let's go back to the printer. Our little print, there's no particular reason I did this one. It was just an interesting looking material that I wanted to print, and that's all it did. So that glue on there really is holding us down. All right, so that's just a PLA, just to print it. Interesting. Oh, here's another one. This one is a PLA. This one's gonna be hard to pick up. It is a polyester PLA blend. It's wanting to focus way back in the background. I'm trying to get it to focus closer, but it doesn't want to. And it's also a pearl. So in person, first of all, it's really hard to see the layer lines on this also, but you can kind of get an idea of the fact that it's pearlescent. So this is from Toner Plastics, and it's a really neat material. The polyester blend in there makes it a little tougher, a little more flexible than PLA. PLA is a lot of times really brittle. So it's about $30 a kilogram, I think. You can kind of see the bottom is, I didn't clear it out. That's some of our carbon fiber left in there. But it's a really, really nice material. It prints a little bit hotter, although I think I printed this at 215, although I'm looking at the bag and it says it's supposed to be 230. So I printed it a little bit on the cold side and it worked fine. But it's a really nice material. All right, back to this. Let's see. We need to get over to our capstan, the top of our feeder mechanism. Over here. So that's what we're going to replace. So this is just attached to it. That's no big deal. This is just the stepper control wires. Here we've got our Bowden tube. I put that in with a wrench, so I'm not going to get that out by hand. Let's find a tool to do that. Oh, none of it does fit, but not quite. All right, so I've already removed the filament so that we can actually get in there. Okay, and there are 4 screws that hold all of this to the stepper. It also is holding the stepper motor in place. So once I take these screws out, the stepper motor is going to want to fall down. So you do have to be ready for that to happen. Let's see if I can find. We have our first previews on our simulation too. Oh, that's too big. Maybe this one. There we go. There are probably replacement screws in our kit, but I'm going to hold on to these just because they might be ones I want. All right, so here, this spring has a adjustment screw, and it's like sitting on top of the one I need to remove, so I've got to take that out, which is the other size. Okay, now I can get that one out. You may or may not want to take these completely out all at once because that means the last one is holding everything up. Now there's one under this arm, and then there's one that's the pivot point for this arm. I got to take the pivot point out first. It's a little bit annoying to do because the Z-axis screw is right there. You can't turn your Allen wrench very easily. So we're also a little bit unstable here, just the way the table is set up. We'll see if we can get this to come out. It's also, you might want to try and get this spring out because that will loosen up the pressure on this guy. Alright, so there's that piece. So notice here is one of the reasons. So this idler is fine, but it's just passive. And what we're going to replace it with is going to be geared to match. We're going to replace that pinch roller. It's going to be geared to match the pinch roller that we're going to put on here so that they're both turning. This one just it's just passive, so it's just applying pressure to keep the filament against the roller there. I have lost the right size Allen wrench. Here it is. Alright, so this one is the last one, and when I remove it, everything's going to come apart. Okay, so we're replacing all of that. We need this though. So here is what I was talking about. This on a lot of the printers lately is just a it's either a press fit or a shrink fit. It's really tight though, so I'm going to have to use my little puller here. I'll see if I can. I got this off of Amazon. Let's see if I can find it for you, and I'll show you. I showed it last time, but just so you don't have to go back and look at that video to find it. Let's see. Here it is. That's the one that I used, or that's this one right here. It's only $10, but you either have to get another stepper motor, or you got to have something that's going to pull this off of here, or you've got to figure out with what tools you have how you're going to get that off of there. And it's not a simple thing. All right, so let's see. Maybe if I turn this around. So this is going to go in here, and I have to put this little guy underneath there, and then it will kind of do that number. I'm trying to get it centered, the little plunger centered on the shaft so it's not off. Alright, so now we have to basically tighten this. It does come with a little little rod here, and that's fine, but it's usually not possible for me to apply enough with this amount of leverage. So I usually have to get something bigger. I guess that one's too big to be able to have enough mechanical advantage to turn this thing. And I usually end up bending the Allen wrench. So it's going to have to be off screen a little bit because I've got to get a lot of torque on it to do it. And you have to also hold, you know, if you just turn it, then nothing happens. So you have to hold this and turn that at the same time, and that's not easy. Let me see if I can find something that's going to help me with this. I might have to take it to the vise over there to be able to do it, or at least to break it loose. Let's see. I might put it on the floor. So, still haven't gotten it loose, but let me show you that, you know, here's what usually happens. So, I might have to get a little bit more leverage. I'll go over to the vise, try to break this thing loose, and then once I get it broken loose, I'll come back. Also, make sure that your pin in the center here is not on the pinch roller you're trying to pull off of there, because if it's on it, then it's just pushing it, you know, it's pushing against itself. All right, I got it off. Bent that. I'll have to straighten that out. But that's the kind of, I clamped it in a vise here, and ended up using a screwdriver with more of a hardened steel shank than the little Allen keys have. Although I might need that particular Allen key to put this back together, so we'll have to go get it, put it over there. So we will have to straighten that out in order for this to work again, because right now it's all, you know, trapped together. It's actually quite warm. So there's your little pulley. It would probably help to heat this guy up, make it expand, and then get that off of there, but didn't do that. Probably would have helped though. So this will work. This guy will work, but it's all it can do to get these things off of here without heating them or anything. All right, but we did get it off. We just gotta, you know, straighten that guy back out. So now what? We've got our new set of stuff here. Now this one does come with a little hand knob that you can, you know, put on here, but I never, for one thing, they're set for a D, so like one that has a flat on here. This does not have a flat anywhere on it, so that's a downside. That most of these little drive wheels are held on with a set screw, and it's assuming there's going to be a flat on here for the set screw to sit in, but these do not. They're completely round shafts. So that's one downside. Here's our top piece. There's our roller. If we need to reverse the direction, there's that. And then here's all the little pieces that we get. So I'm going to put all these pieces in here so I don't lose them. Okay, here is our actual, that's why I wanted to put them in the box. Here's our actual new drive wheel. So it's going to have to go on here, and it does have one set screw. It's already kind of tight, and they did give us an Allen that will fit that in case you didn't have one. So one thing you have to do here is you do have to get this lined up with this. See how they're geared together? Is now both sides, you know, the stepper is going to turn the one in the center, but it's going to be geared to this one, and they're both going to drive the filament at the same time. So I'm going to measure this diameter. So I'm going to measure this diameter because the way Clipper does E-steps is it doesn't do E-steps. It does rotation distance. And rotation distance is how far does an axis move when the stepper controlling it moves one entire revolution. So basically, rotation distance for the stepper motor, or for the feeder, is going to be how much, it's going to be the circumference of the drive wheel. So it looks like we're at 7.39, probably 7.4 is what it's supposed to be. So 7.4 millimeters is the diameter. So we can use that to calculate the rotation distance. Let me write down 7.4 before I forget that that is our diameter. Okay, so we'll use that in our configuration file in a minute. Let's see what else we have in here. We have springs. We have some of these little guys for our Bowden tube. Looks like this is going to hold the Bowden tube onto our printer. Originally we had one of these, which is not going to match up there, right? So we got to get this guy off. Sometimes it's easier just to cut here, but let's see if we can pull it off of there. All right, so it did come off relatively easy. Sometimes there have been so many like little burrs on our Bowden tube that you can't get this to slide off, but that time it did come out pretty easy. Okay, let's see. I'm seeing one other. Oh, this is this odd looking one is our hinge, so it's going to go in here, right? And then there's another special one, or well, it looks like there's three special ones. And so it doesn't matter. They're all the same. But usually there's one that is countersunk so that the hinge can clear it when it goes over it. But they're all countersunk on this one. All right. So let's rotate this back around and put things back together. Let me check on our... Oh, we've got one still going, but a lot of our studies have completed. Some of them converged to an actual solution. All right, but let's finish up this guy. So here, you do want to keep track of this plug so that you're not having to, like if you put this over here, your wire has to wrap around, so that's annoying. So try to make sure you put the plug in a convenient spot, which here is probably the most convenient, although you could say that that way is also convenient. So let's get this guy and find there. A little bit hard. I'm doing the most annoying one first. All right, so it's hanging there, so we can put some of these others in. Don't tighten any of them up until you've got them all started. Oh, wait. Yeah, I guess that is the right way. Okay. Okay, so this one I have to tighten because the little lever arm's going to cover it. So I'm going to tighten that one without putting that one in. I think we'll be able to tighten all of these. They don't have to be like super tight, but you don't want them loosening on you. So now this is going to sit here. And this is where we need to get this guy lined up with it. So I'm going to put it roughly in place. We haven't put our spring in yet. You know what? I think I do need to loosen these up because they're keeping that one slightly aligned wrong. All right. And the shoulder bolt fell out. There we go. Now let's see if we can get this to, there we go. Now we can tighten this guy up because it's going to get covered up. And we can tighten this one. It is, I haven't seen it on this style, but this, wherever this hinge is, if you tighten it too much sometimes, it will actually bind up your lever. So right now we're way loose, but be careful not to over tighten it. All right, so we want to get these lined up with each other, and gotta find where that set screw is and tighten down this guy. Okay, no, that's too high. There we go. Okay, let's tighten our hinge now and make sure that everything's still lined up. It looks like it is. We need our spring in there. So our spring is these three pieces. And this one works differently. So the spring, oh no, is it gonna not clear? Oh no, it did. Good. So the spring actually sits on this side, and the little thumb wheel to tighten it sits on this side. And in general, I mean, you can tighten this to have more pressure or less pressure. In general, if you have it where the thumb wheel, the screw, you know, the screw that's in the spring there, if that end of the screw is about flush, I've got it a little bit more than, you know, it's a little proud. If it's about flush, then that's a good starting point. But if you need more compression, you can tighten it up more. If you think it's really loose, then you can loosen it. If it's really tight, then you can loosen it. So I just use it where it's about even. But to load filament, you'll have to actually pull this one, and that will pull the this wheel away from this one. Okay, we need our fitting here now. So this little guy is going to go on. Oh wait, first that little guy is going on. That one, and this is going to go. Now you're not going to be able to see this very well, but you can push this in too far to where it gets chewed up by the roller here. So try not to go too far with it, and then we just tighten it down. You want it as close as you can get it, and I think I could probably, there we go. Okay. And I had that big wrench. Here it is. I think oh, it's so close. Well, for now we'll just hand tighten that, but I do need to go back and tighten. Now, all that's left is to find out if I need this or not. So, I can plug it in, turn it on so the steppers can move, and then we'll go over to our console. So I'm over here, that one, over here, and it's not going to extrude any filament unless I have it heated up. Even though there's no filament in there, it will not let it move because it thinks that it's too cold to extrude filament. Let's go ahead while we're at it, and let's go to while we're waiting for it to heat up, go to our printer config and find the extruder. So rotation distance, let's just comment that out, and then let's calculate with a calculator, which I am not, there's one. The circumference, we measured the diameter of our drive wheel being 7.4 millimeters. Let's just, pi times diameter is circumference, so multiply by pi. 23.24. Looks like we can use 3 decimals. 248 is our new rotation distance, and we will save and restart. We'll have to tell it to keep heating up because it's going to go back to 0. We're at 170. I think we set it to where it would extrude at 175. So what we want to know here is, are we turning the wheels the right way, the pinch roller? Are we turning it the right way or not? So right now I don't, right now I don't have the reverser in there, and we're just going to extrude and see if it's extruding or retracting. So alright, that should be an extrude, but you can hopefully tell by the direction it's going that would actually retract filament. So to fix that, you could reverse the, I think, middle 2 wires here, but you know what, we're just going to use this. Now we're going to try and extrude again, and it's going the right way. Oh, so I think that sound was grinding on our Bowden tube. I must have it too close. Let's back it up a little bit. There we go. Try it again. Oh no, it's binding on something else. Or this is not quite lined up. I know it's a little blurry. We're kind of close to it. We might have to adjust that again. Let's see if I can find the set screw for it. It's all... I think what's happening, could be wrong. Let me turn the motors off. Where's motors off? I don't know. I don't know where motors off. I don't have a macro for that yet that I see. Macros in print. I could do that. Maybe that'll turn them off. Nope. I'll just turn it off. All right. I think it could be that our set screw is actually colliding, but let's try and adjust on that and see if that's a problem or not. Yeah. So what is it hitting? I think it's hitting... Oh, you know why? Because there's no filament in there. So I think there's not enough clearance between our set screw and the other roller. Let's try putting some filament in there. So I'll have to turn it back on and see if that will give it enough clearance. So you can see how to load. Okay. Let me give it some temperature so it'll let me do that. having a little bit of issue because I haven't clamped that down yet. I may have to get that to clamp down first, but right now we'll just do this. There we go. We can always like feed it that way. Alright, so that put a little bit more space between those. Alright, let's see if it likes to extrude now. Yeah, so there's just that much tolerance, or that tight of tolerances, where the set screw holding this guy without filament in there, which, you know, the filament spaces this out just a little bit. Without that filament in there, it actually, the set screw collides with the other side of the pinch roller, and it won't go around it. So looks like with filament it's fine. It must be super tight tolerances on there though, but it looks like it's fine with set screws. Now what we'd want to do, just to check that our rotation distance is correct, easiest way to do that would be to come in here, chop this guy off, and ask for a certain amount of filament. So I'm going to ask for 50 millimeters of filament, and then measure what we get. So let me zero my calipers, and I'm going to have to cut it out of there to measure it. It's a little bit curled up, so there's going to be a little error, but I'm trying to flatten it and measure it. And that's exactly 50. I mean, for the 50.3, but that could be the fact that, you know, I cut it and it's kind of bulged on the end there. So I'm thinking our rotation distance is correct. And now we've got a new feeder, dual-sided, all-metal feeder. This doesn't change anything on the ability to print other materials, but it does, oh, I can't get it on the filament there. It does give us a little more accuracy on feeding how much material we think we're feeding. We're driving from both sides. This could help if we want to print more flexibles, although we were able to print flexibles, but there are, where's it at? There are really flexible flexibles. I just don't see it right now. I haven't shown it on the stream yet, but there are some flexibles that are like rubber bands. So they have a hard time printing on this kind of printer anyway, but this could help. All right, one other thing, and then let's look at our results here. So here, not there, here are what we that one, or where we have our recommended outcomes. They all look generally the same. This one looks kind of similar to what we got in Fusion 360, right? So what you would do is here or down here are the same ones. Looks like there's a fifth one that it didn't like. But you know, I have some of these are casts, some of these are additive. We can pick one, and we can, you know, view it up close. This one has some of those same, you know, that little notch in there that our SolidWorks version had. You can, from here, you can create a design based on this, or a mesh if you want to just take a mesh. Normally, you wouldn't want to like just use this. You would want to use this as a guide to actually engineer the part, but you know, there's kind of the idea of generative design in Fusion 360. Oh, I didn't remember this. So you can actually watch the steps that it went through to get to these things. So maybe there's an intermediate step that you like somewhere in there. So that's kind of how it works with generative design. It didn't take that long. And the difference here is I simultaneously got 4 recommended outcomes. It looks like there are 5, and one of them it didn't like. But there are multiple outcomes because you're sending this off to the cloud versus having to use your local processing power on your computer to do this. Would I use any of these as a connecting rod? I have seen some connecting rods that look similar to these, but you can at least get some ideas, a little bit of thought on, oh, I could do this. Now these did not, get very spider webby. Sometimes when you're really trying to lightweight apart, the things get really spider webby, but we put 10,000 pounds of compressive force on this, so it can't remove a lot of material and still function. Maybe if I put a lighter load on here, then we would have got some of the more fancy designs that look, spider webby. All right, so that's Fusion's generative design. Last time we talked about SolidWorks topology optimization. They're doing the same kind of thing. And they don't have to apply to additive fabrication. In fact, the Fusion version will let you pick other modes of manufacturing, casting, additive, 3-axis, or multi-axis milling, or 2D cutting. So you can get some different options from it. SolidWorks just kind of, hey, here's the design, you figure out how to make it. Although I think maybe there's some controls. We didn't use them, I don't think. Anyway, we have also changed out our feeder on our printer. I'm going to put it in the box. So I'm going to put it in here, and we're going to start printing some of our filament. So this is our filament. Oh, so this filament is very hygroscopic. So it wants to absorb moisture from the atmosphere. So I'm using this guy, a vacuum bag kit. It comes with a little vacuum pump and I don't know how many, some number of bags. Didn't say on the box how many. There were multiple bags in there, maybe 5 of these special bags with a port on them where you can vacuum seal your filaments that are going to absorb moisture. So nylons and polycarbonates and TPUs, they like to absorb moisture from the air, particularly if you're in a place where average humidity is 70% at least. So that's a pretty cheap way. There are much fancier, like food vacuum sealer type things, but this is a pretty cheap $20-ish solution if you're trying to create a dry box type of situation. You can get a little dry box, put some desiccant in it, and suck the moisture out that way if you want to. There are processes where you can bake the moisture out, but those are, you have to have some tightly controlled temperature situations, and you have to bake for a long time. The problem ends up being that like an oven, first of all, you'd be baking plastic in your oven, which is generally not good, but a kitchen oven has trouble at the lower temperatures, and it's easy to get high enough that it starts melting the spool itself that the stuff is on, and you just end up with a big mess. So I would, unless you have a furnace that has nice temperature control that you can leave on for 6 to 8 hours, I would just say keep your stuff in a dry box of some sort, so that you don't have to worry about it absorbing moisture. If it gets moisture, I do have a solution we'll look at next time on how you can deal with that. But we're out of time today. We'll be back later, Friday, I suppose. And I think what we're going to do Friday is a little bit of modeling type stuff. Hopefully, we have at least one part of our violin done. We'll see how that goes once we start doing more than a single wall vase print. But we'll see how that goes. All right, I'll be back Friday.